Okay, guys, I think it's time to start. Just in case, as usual, if you have any questions, you may ask them during the lecture, or you may post your question in the chat.
Excuse me, there are only 20 of us now, so maybe we can wait a couple of minutes, just everyone to participate and to join the conference.
Okay, that's a good idea, but okay, let's wait for a minute or two. I think it's a good idea, but then we have to finish a bit later. I hope that's okay. Okay, I believe we can start like in a lazy manner. So I'll try to remind you where we left off. So okay. So at the end of the previous lecture, I formulated a claim, but didn't prove it. So I want to recall the statement. So suppose we have a group G, and we have an element G small from G capital. Then there are two options. The option number one, all powers of the element are distinct. So for all possible integer, like for all distinct integer numbers, G to the m is different from G to the n. And the option number two, there is an integer n, there is a natural number n, a non-zero natural number, such that the elements 1, G, and so on, G to the n minus 1 are distinct. And G to the n is equal to 1. So in the first case, we have that the cyclic subgroup generated by the element G consists of distinct of all possible powers of the element G, and all the powers are distinct. So these are all the elements. And in the second case, the cyclic subgroup consists of the elements like this. So this claim describes all possible cyclic subgroups. So there are two options. Either all, so just by definition, a cyclic subgroup generated by an element G is this set, the set of all integer powers of your element. And there are two options. Either all these elements are distinct, or well, they are repeated in cycles. So you may find such an integer n, such that G to the n is 1, and the powers from 0 to n minus 1 represent all possible elements here. So all other powers coincide with at least one of them. Okay, so these are your options. So if are there any questions regarding the statement?
How do we call those groups?
What again?
How do we call them? Like we have first type and the second. How
do we call these two options? There are no names, like the option number 1 and the option number 2.
And the only idea that we have different values for different powers, and we have G to the power n equals 1, right?
Could you repeat the second thing?
I mean, it's the whole idea that we have two different types.
We just have two different options, either this one or this one, and that's it.
Okay.
Excuse me, so like this don't both hold at the same time as I see it.
What again?
both of these do not hold at the same time.
Yeah, they do not hold at the same time, because in the first case, there are infinitely many elements in the cyclic subgroup. In the second case, there are only n elements in the cyclic subgroup, and n is finite. So yes, these two options are mutually exclusive.
And each element of the group is can be defined by one of these options.
Again, which element what?
Each element can be defined by one of these options. Like each element.
Yes. Like, one of them must hold for an element.
Oh, I see.
So there are no other options.
I'm sorry, could you please repeat what is written in the first statement?
Okay, for all distinct integers m and n, the powers, the corresponding powers of the elements, of the element g, are also different.
Okay, thank you very much.
So, yep.
One more little question. Am I right that we can find the cyclic subgroup for any element?
Yeah. You may generate a cyclic subgroup for any given element. So this is not an issue. So if you have an element G, then this thing exists. But then the question is, what is its structure? Or, what are the elements there? And there are two options. It's either infinite and all powers are distinct, or it's finite, and then these are all, well, these are distinct, all distinct elements in your cyclic subgroups.
Okay.
May I ask another question, which might be even worse than the previous one, but still. In the first option, when you describe a cyclic subgroup, you include the inverse elements.
Yes.
And in the second option, you discard them, like they're not inside.
Okay, let me be more precise. So in both cases, the definition of the cyclic subgroup is exactly the same. So just by definition, this thing consists of all possible powers. Like there is no difference. So you have to take all of them. But the claim says that if you take these guys, then all other powers coincide with these guys. For example, g to the n is the same thing as 1. G to the n plus 1 will be exactly the same thing as g. G inverse will be exactly the same thing as g to the n minus 1, and so on. So, I mean, these are just representatives of all the elements in the cyclic subgroup. So some of the, so it describes the way the elements coincide with each other.
I see, thank you.
Okay, so it doesn't mean that you don't have G inverse here. It means that G inverse will be one of these guys. And specifically, G inverse coincides with G to the n minus 1. Okay, I hope now it should be clear, but just in case, are there any other questions regarding the claim?
No.
Okay, so let's try to prove this. Oh, yeah. Okay, so now, well, suppose we have this element G here, and we consider this guy. So the option number 1 is when all the elements are distinct. So if all the elements are distinct, then this is the option number 1, and we are done. So we may suppose that for some distinct integers m and n, we have g to the m is equal to g to the n. So this is the contrary condition. So if this happens, then, well, we may compare m and n, and we may suppose that, for example, m is strictly greater than n. Then now just multiply this equality by g to the n inverse, g to the minus n. I'm sorry. Just multiply this equality by g to the minus n, and you will get g to the m minus n equals 1. This is according to the rules how to multiply powers of an element. And now we see that if for some two elements we have that their power, the corresponding powers are the same, then we can find a non-zero natural number, which is m minus n. Let's denote this number by k, such that g to the k is equal to 1. So this is what we have done. So there exists a natural non-zero number k such that g to the k is equal to 1. Now we may consider the smallest possible k with this property. And let's say n is the smallest. K such that g to the k is equal to 1 and k is positive integer. So now I want to prove two things. First of all, that each element of the cyclic subgroup coincides with one of these elements. And the second, so if I take an arbitrary element from here, let's say g to the m, then it must be one of these guys. And the second thing that I want to prove is that all these guys are distinct. They are different. And then, this will be the proof. Okay, so the step number 1, we want to show that if we're given g to the m for an arbitrary integer m, we can find an r between 0 and n minus 1 such that g to the m is equal to g to the r. So let's divide the integer m with remainder by the integer n. And we will get m is equal to q times n plus r, where the r is a remainder. And we know that by definition of the remainder, it satisfies these conditions. So it's exactly between 0 and n minus 1, including 0 and n minus 1. And now we can rewrite this expression in this form. And also, according to the rules of multiplying the powers of an element in a group, we will get this. And then we will also get this. But now, by the definition of n, g to the n is equal to 1. And then 1 to the power of q is also 1, so the result is g to the r. So as we can see, the element g to the m is equal to the element g to the r for some r between 0 and n minus 1. So this simply means that every element from this subgroup has one of these, is just one of these. So the second part is to show that these guys are distinct. So let's suppose that the contrary holds. So this was the part number 1. And the part number 2 is to show that these guys are all different. So suppose that for some powers a and b, we have this, where a and b are between 0 and n minus 1. Then again, we may assume that a is strictly greater than b, or and they are distinct. In this case, multiplying by g to the minus b, we will get g to the a minus b is equal to 1. And now a minus b, by definition, is strictly smaller than n. Why? Because they were positive integers strictly smaller than n, and since a is greater than b, their difference is also strictly smaller than n and is positive. So we have found a number, well, which is like n prime, such that g to the n prime is equal to 1, but it's strictly smaller than n. And this contradicts to the choice of n. So where did we get that contradiction from? It came from here. We assumed that we have two elements here that are the same. So since we get a contradiction, the assumption was wrong. So this completes the proof. Just in case, are there any questions? Should I repeat something or clarify details?
Can you clarify the second part of this again?
Oh, okay. Okay. So now we have these elements. So the 0 power, the first power, etc., to the power n minus 1. And we want to prove that all these elements are different. And well, let's take let's assume that this is not true. Let's take some element here, which is g to the a, and a different element with a g to the b, which is here. So a and b are two different numbers between 0 and n minus 1. And let's suppose that they are the same elements in the group G. So then you do exactly the same trick as we did here. You just multiply this equality by g to the minus b, and you will get this thing. And now, what do we have? If we denote a minus b by n prime, we have g to the n prime is equal to 1, but n prime is strictly smaller than n. And as you can see by the definition, n was the smallest possible non-zero, well, positive integer with this property. So if we have found an integer, positive integer with this property, which is strictly smaller than n, then we have a contradiction. So we've got a contradiction here.
I see. That's quite clever. Thank you.
Okay, are there any other questions?
Yeah. I didn't really get why a by b is less than n. Why n prime is less than n?
Oh, why a and b are strictly smaller than n?
Yes.
Okay, by definition, we've got these elements from here. So let me write it here. So we have this set of powers, the 0 power, the first power, the second power, etc., to the power n minus 1. And we take two elements from here. One of them is g to the a, and the other one is g to the b. But as you can see, here we have powers from 0 to n minus 1. So a is between 0 and n minus 1, and b is also between 0 and n minus 1. So I want to prove that these elements are distinct. So
yes, but here we multiply them at or minus between.
Oh, why a minus b is strictly smaller?
It's a minus b or a multiplied.
I'm sorry, there is a problem with the sound.
Yes. Well, no, it's quite logical. It's fine. Okay, it's fine.
Just in case, is the question why a minus b is strictly smaller than n, or what?
No, I think the question is what sign is there?
Oh, because a is strictly larger than b.
No, I think they meant the sign in a minus b minus isn't all that long, I think.
Oh,
and you're mistaken for a multiplication sign.
It's not a multiplication. Yeah. Oh, okay. I see. So we multiply by g to the minus b this equality, and we will get g to the a minus b on the left-hand side. Is it clear now? I mean, was that a question, or should I clarify something else?
Yeah, that was my question. Sorry for sound. Thank you. I understand now.
No problem, no problem. So, okay. So
I have one question.
Yep. Okay.
Could you repeat the idea? What you have done?
Okay. So first of all, what do we want to prove? We want to prove that if we're given a cyclic subgroup, then we have two options. In the first option, all the elements here are distinct. And in the second option, we want to find an integer n, which is positive integer, such that the generator raised to this power is equal to the identity element, and all powers between the 0 power and the power n minus 1 are distinct, and any other power coincides with one of them. So this is a description of a cyclic subgroup. And now, so how do we prove that? So, well, we assume that some powers are the same. So like for some m and some n, we have like g to the m is equal to g to the n. And starting from that, we can find an integer, positive integer n, the smallest possible, such that g to the n is equal to 1. And after doing that, I'm proving that this n is exactly the n I should take here. That is, well, first of all, g to the n is equal to 1, which is just by definition. And the second part is to prove that every power from the cyclic subgroup belongs to the set, and all the powers here are distinct. And this is exactly what is proven here. Is this enough, or?
Yeah, thank you.
Okay. So now I want to describe subgroups in the group Z with addition as an operation. So claim. So let's take Z with addition, and let's assume that H is a subgroup. Then there exists an integer n such that H is equal to n times Z, which is by definition consists of elements of the form n times k for all possible integers k. So every subgroup of the group Z has this form. So you just take multiples of a fixed integer n. Okay. Well, first of all, we want to show that every subset of this form is actually a subgroup. So the step number one is we want to take an arbitrary subset of this form, and we want to show that this is a subgroup.
Excuse me, may I ask a question
Yep.
before we start?
Yep.
Am I correct in like assuming that this claim means that each subgroup can be described by multiplying the whole group by a certain scalar?
Yep. So I take an arbitrary subgroup H, and then the subgroup is of this form.
Mm-hmm.
This is exactly what you're saying. Yes, exactly.
Okay, thank you.
So there are no other subgroups. So these are all possible subgroups. And this is really convenient. So in order to fix a subgroup, we just fix an integer and take all multiples of this integer, and this gives us a subgroup.
So
yep.
We have such an integer for every subgroup?
Yep.
All right.
So this is exactly what's written here. For every subgroup, there exists an integer n such that it has this form. Are there any other questions? Okay. So, okay, let's check, first of all, that this subset is a subgroup. In order to check this, we want to show that this set is closed under addition, because this is our operation here. We have the neutral element inside the subset, and it's closed under taking the inverse elements. So if we take two elements from here, they are of the form n times a and n times b. and the sum of these elements is of the form n times a plus b, so it's also inside this subset. Also, the 0 element is of the form n times 0, so it's also inside this subset, n times z. And if we're given an element na, then its inverse is minus na, which is n times minus a, so it's also inside this subset. So the subset satisfies all the conditions of a subgroup, so this is a subgroup. So that was an easy part, the part number 1. Now, the part number 2 is how to show that there are no other subgroups. Well, suppose we're given a subgroup H inside Z. So we want to find this element N. Well, let's let's define our element N in the following manner. We take so let's take the smallest positive integer in H. Well, there is a question. Are there positive integers in H? Is it even true that you can find a positive integer in H? Well, it may happen that there is no positive integers, but let me explain what to do here. So suppose, the case number 1, let's say it like that. The case number 1, the subgroup may consist of the 0 element only. In this case, it's clear then that H is equal to 0 times Z. And we're done. So now we may assume that there is at least one non-zero integer inside H. So there is some integer n which is not 0 and it belongs to H. If n is strictly smaller than 0, then since H is a subgroup, the minus n element must also be inside H. So in this case, so if H consists at least one non-zero element, it must contain at least one positive integer. So because of that, this definition is well defined. So in this second case, we may take n to be, this guy, the smallest positive integer inside H. So there could be many different positive integers inside H. So we take the smallest possible. So now we have that n belongs to H. But okay, just in case, are there any questions until this moment? Should I clarify?
One question, what about the case if we don't have any integer?
Yep. Oh, again, so let's start from this line. So the case number 1, H consists only 0 element. Well, if H consists on only 0 element, then H is equal to 0 times Z. So, and here we're done. The second case, H consists at least one non-zero element.
Okay, it's clear. Ignore it.
Yeah. And in the second case, H must contain at least one positive element.
I'm sorry, can I ask a question?
Yep.
So why, if n is smaller than 0, then minus n also has to be an element of H?
Okay, because H is a subgroup. So if it contains an element, its inverse must be also inside this subgroup. So,
sorry.
No problem. So if n belongs to H, then its inverse, which is minus n, it also belongs to H.
Oh, all right, thank you.
Yeah, because it's a subgroup. Are there any other questions?
If in the second case we have our n less than 0, why do we say that it is the smallest possible integer? This
No,
the
no.
smallest positive integer.
Okay, no, oh, there is like a collision of notations. Let's say it's like n prime here. So n prime is some, so what I'm saying here is that if you have at least one non-zero element, you have at least one positive integer element here. And then you consider only positive integers inside H, and you take the smallest positive integer inside H. And this is your n.
Okay, thank you.
Are there any other questions? Okay, I hope now it should be clear, but okay, let's proceed. So where are we now? So now we know that there is some, so we have found an element n in H such that n is strictly greater than 0, and there is no elements of H between 0 and n. So if you take any element m between 0 and n, so it's not inside H. So this is the property we have here, because n is the smallest possible positive integer between 0 and n, or inside H. So now I want to prove, so let's prove that H coincides with n times z in this case. Well, when you need to prove that two sets coincide, you need to prove two inclusions. The inclusion number one is this one. So we want to show that the right-hand side belongs to the left-hand side, and the inclusion number two is this one. We want to show that H belongs to the right-hand side. So let's prove this one first. So we know already that n is inside H. But now if you multiply n, well, just by definition, n plus n plus n, k times must be inside H, because H is a subgroup. So n, which means n times k belongs to the subgroup. Then n times 0 means the 0 power, which is 0, is also inside H because it's a subgroup. An element minus n also must be inside H because it's a subgroup. And if you add it several times, like k times, you see that minus k times n is also inside H. So all multiples of n must be inside H. So this proves that n times z belongs to H. Okay, so the second claim is to prove that H, the other thing, that H is actually a subset of n times z. So this is what we want to prove now. So how do we do that? We should take an arbitrary element H from our subgroup. This is an integer number. And we want to prove that n divides this number H. Well, let's try to divide H by n with a remainder. So we can write H is equal to Q times n plus R. And here, because R is a remainder, we have these inequalities. Oops, like this. So R is between 0 and n minus 1. And now we can rewrite this as R is equal to H minus Q times n. And as you can see, by the choice, this guy is in H. So this is here, by our choice. Also, this element is an element of n times z, and we have already proved that all elements of this form are already inside H. So this guy is also inside H. So the difference of these two elements is also inside H, because H is a subgroup. It must be closed under multiplication and taking inverse elements. So here we have that the element R is also inside H, but this element is between 0 and n. But here we know that this element cannot be non-zero because there is no element of H between 0 and n, not including n and 0. So the only option for the element R is R to be 0. So because by the choice of n, the only option for R is to be 0. And this means that H is divisible by n. And this completes the proof. Okay, just in case.
Could you repeat? Yeah, it's clear, but could you again repeat the idea?
Okay, so
of the proof.
Both cases or just the later one?
Both.
Okay, the case number one, we want to prove that this guy is inside this one. So we know by the by the choice of the element n that the element n itself is inside H. But now we know that H is also a subgroup. So if you add if you just apply, what's written here is actually a power of the element n, but in an additive notation. But if you have an element inside a subgroup, then every power of an element is also inside the subgroup. So what's written here is that a positive power, a 0 power, and a negative power is inside the subgroup H. And the second part is to prove the inclusion. And here we take an arbitrary element from H, and we want to prove that this element is divisible by n. So we don't know if it's divisible or not, but we can divide the element H by n with a remainder, where R is our remainder. And now we see from this equality that R itself is also an element of H, and this element is between 0 and n. But because of this property, we see, you see, R is a non-negative integer smaller than n inside H. But n was the smallest possible positive integer inside H. So the only option for R is to be 0. Because if it were positive, there would be a contradiction with the choice of n.
Okay.
Good.
Okay, I still don't understand. In the beginning, we wanted to prove that every group, every subgroup can be represented in
this form.
In this form. I don't understand the proof. We found the smallest integer. We proved that it exists in every subgroup, and what? No,
the existence of this element was shown here, but
yes.
Here we prove that for this specific element, H coincides with this subset. This is exactly what we wanted. And here is the proof of this equality.
Okay, but we assume that H is equal to n by that.
No, it's not an assumption. Okay, this is what's probably misleading. Let's prove that. So this is what we want to prove. No, this is not an assumption. I'm saying let's prove that H is equal to n times z. In order to prove this equality, we need to prove two inclusions. And here I prove two inclusions. This is a subset of G, and this is a subset of the set of integers. This is a subset of integers, and we prove that these two subsets are the same.
Okay, so we find the smallest integer. We show that for any k from that we can find an element in H, and for any element in H we can find an element in that. Like we show that.
What's your question? Okay, so let's do it like that. So let's skip this, and later on, if you still have questions, I'll just write to me, and I will explain it to you personally. Okay. Okay. So let's move on. Okay, so now I want to discuss something what is called cosets. Well, it happens that it's not enough to study subgroups of a group, but we have to find, well, some more appropriate tools. And Cosets is our tool. It will be the main tool for us. So let me give you a definition. So suppose G is a group. And H is a subgroup. And we're given an element G in G capital. Then a left coset of H is this, is the set given by this formula. So we just take an element G and multiply by all possible elements of the subgroup H. And this is a left coset, or the left coset generated by G, or the left coset of the subgroup H with respect to the element G. So this is the left coset of H. So the left means that the element G small is on the left of the group H. In the same way, we may define a right coset. A right coset is the set of all the elements of this form. This is a right coset. So the word right means that G appears on the right. Okay.
So, sorry,
Yep.
so is it for not abelian subgroups?
Well, in case of abelian subgroup, there is no difference between left and right cosets. Each left coset is exactly the same thing as the right coset. So in abelian case, you just there are no differences between these two things.
Okay,
So
thank you.
yeah. So for example, if you take G to be Z, this is an abelian group, and you take H to be 2Z, which is the set of even integers. This is a subgroup in G. Then you have two different cosets. The first one is 2Z, the set of integers, and the second one is 1 plus 2Z, is the set of odd integers. So this is even, and this is odd integers. So these are, well, these are examples of cosets. So this is a coset, like, well, you should write it like this. So you take an element G, here it's 0, then you have your operation, and then you have a subgroup. So here operation is addition, so you just take 0 plus subgroup, or you may take 1 plus subgroup, or you may take any other number like 42 plus 2Z. These are examples of cosets. And here, there is no difference between left and right cosets. Every left coset is a right coset and vice versa. Okay. Well, in commutative case, there is no difference between left and right cosets. But in non-commutative case, there is a difference. And because of this difference, we have another definition. Well, if it happens that, well, let's say we have a group G and a subgroup H, and if all left cosets are exactly the same as the right cosets, in the sense for every G small from G capital, the left coset for the element G is exactly the same as the right coset for the element G, then we will say that H is a normal subgroup. So this is just a property of a subgroup. Some subgroups are normal, the other ones are not. For example, yep, again.
Like I've kind of forgotten. Is normal synonymous to abelian?
No. G is an arbitrary group. Let's say G is an arbitrary group, and H is an arbitrary subgroup. Well, if G is abelian, then every subgroup is normal, and then it's not an interesting property. But if G is non-abelian, some groups are normal and other ones are not. Let me give you an example. I hope that the example will clarify the details. Let's take G to be S3, which is the group of permutations on free elements. Then you may take H to be the cyclic subgroup generated by the cycle 1, 2. So we permute 1 and 2 and leave 3 as it is. And we may take H to be the cyclic subgroup generated by the cycle 1 to 3. Then you may check that this group is not normal. And this one is normal. So I want to leave this verification to the seminar, but this is an example. So you may check that left and right cosets of these subgroups are not necessarily the same, and all left and right cosets of this subgroup are always the same. So this is just a property of a subgroup. Is it clear now? Should I clarify something? Okay. So the next question is how to determine if a group is normal or not. I mean, how to check that. And here is the way to check. Oops. If we have a group G, an arbitrary group, and an arbitrary subgroup H, then the following conditions are equivalent. The condition number 1, each left coset coincides with the right coset for whenever G is an element of G capital. The condition number 2, G inverse coincides with H for each element G in G capital. And the condition number 3 is G inverse belongs to H whenever G is in G capital. So these are 3 different conditions and they are equivalent. So the first one is actually the definition of H being normal. So this is exactly H is normal. So the other conditions is the way to prove that H is normal. And the third condition is actually the one that people usually use the most. So this is the most useful way how to check if a subgroup is normal. I'll clarify the notation here just in case if it's not clear what I mean here.
Excuse me,
yep.
Yet another question. Am I correct in assuming that basically a coset is a subgroup? Because the way it's defined, as I see it, it is this group multiplied by a scalar, an element from that group.
Okay. No, it's not true. It's not true. Okay, let's say here a remark. A coset is if you take an element G from G capital from A minus H, so let's say you have a group G and a subgroup H and an element G here, then a left coset, the left coset and the right coset, they are not subgroups. Why? Because the identity element is not here. Indeed. Let's check this. Well, if the identity element is here, then it simply means that 1 is equal to G times H for some element H. And then multiplying by H inverse, we will get G is equal to H inverse, and this is inside H, which is a contradiction because we assumed that G is not inside H. So this is what happens with cosets. So if you generate a coset by an element outside of the group H, then you will never have a subgroup. But if you take an element G inside a subgroup H, then G times H is actually the same thing as H itself.
Yes, I see. Thank you.
Okay, so yeah, so roughly speaking, the only coset which is a subgroup is H itself. The other cosets are not subgroups. Okay, so let's go back to the claim. So now I want to prove that these three conditions are equivalent. Well, let's try to prove that 1 and 2 are equivalent, and then I'll prove that 2 and 3 are equivalent. So 1 and 2 is relatively simple. So what do we have? We want to prove that GH equals HG for all G is the same thing as GH G inverse equals H for all G. But just in case, when I write this, I mean GH G inverse by definition is G times H small times G inverse for all H inside H capital. So this is just by definition what this means. So let's show how this is done. Well, if we have this equality for a particular element G, so these are two equal subsets of the group G. And inside the group G, we have a map which is multiplying by G inverse on the right. So if we apply this map to exactly the same subsets, well, to equal subsets, the result will be equal. But when we apply it to the left-hand side, we will get GH G inverse, just by definition. And when we apply it to the right-hand side, we will get H. And if we, if we multiply by the element G on the right, so we can go from the right-hand side to the left-hand side. So this is the proof that 1 and 2 are the same. Just in case, are there any questions regarding this? Okay, so now we want to prove another claim, which says that GH G inverse is equal to H is the same for all elements G, is the same thing as GH G inverse belongs to H for all elements G from G capital. Well, it's clear that the left-hand side implies the right-hand side. This one is clear. So the interesting part is the other implication. So this is what I want to prove. So now, well, we know that this inclusion holds. Let's multiply this inclusion by G on the right. Well, again, well, if the left-hand side is a subset of the right-hand side, when we apply a map to both sets, then the smaller one remains inside the larger one. So when we apply multiplication on the right, we will get GH belongs to HG. And then we apply multiplication by G inverse on the left. And we will get H belongs to G inverse HG for all elements G inside G capital. But since this is true for all possible elements G, I can take G to be G inverse. So I may substitute G inverse instead of G. So this holds for G inverse. So since it holds for any element, so it holds for G inverse. So this is what we can show. But then G to the minus 1 to the minus 1 is exactly G again. So we have H belongs to GH, G inverse. And as you can see, we started, and this also holds, so the latter inclusion holds for all elements G in G capital. So we started from this inclusion, and as you can see, we proved the other inclusion. So the well, if you switch these guys, then the right, well, the left-hand side here is the right-hand side here, and this is exactly the opposite inclusion that we needed. And this completes the proof.
I have a question.
Yep.
How did we go from G inverse to G? Like, how can we substitute?
Okay, so why can we substitute? Let's try this in the other way. So we have H belongs to G inverse H G. Yep, and this is true for any element G from G capital. For example, I can take G to be H inverse for some element H. Like, so since it's true for any element G, I can fix an arbitrary element H, just fix an arbitrary element H. And since this is true for any G, I can substitute H inverse instead of G. So I will get H belongs to H inverse to the minus 1, H minus 1. But here, H is a terrible name for an element here because I do not assume that H belongs to H capital, but it's just an element of G. So after doing that, I see that H belongs to H small, H capital, H inverse. And H small was an arbitrary element of G capital. So I just can rename it, like, you know, it's like a variable. So H means an arbitrary element. So I can denote it by any name, like H, G, T, S, or whatever. So it holds for any H in G. So you may rewrite it like H belongs to GH, G inverse for any G in G capital. Is it clear now?
Yes, thank you.
Okay. Whew. Let's go further. Okay, so let me summarize what's going on here. So we, if we have a group G, we may, and its arbitrary subgroup H, we may generate subsets called cosets of the group G, of the group H. Here, so this is the definition. And so these are the left cosets and these are the right cosets. And now we have discussed a question when the left and the right cosets are the same. So this is what, so that's what we have discussed here. So now, let me show you some properties of the cosets, of the left and the right cosets. So if we have a group G and a subgroup H, so let me draw a picture. So suppose this is your group G and you have a subgroup H here. So this is just a part of this set. So what I want to show you that the cosets, well, they form a partition of the group G. So if you form all possible left cosets, you will get something like this. So all distant cosets, they do not intersect and they cover the whole group. So this is what I want to prove. So G is actually a disjoint union of all possible cosets, or left cosets. And exactly the same happens when you take the right cosets. So the subgroup H is here, but the right cosets may be different from the left cosets, so the picture will be something like this. So the group G is also a disjoint union of the right cosets. So this is what I want to show you. And also the other thing that I want to explain, that the amount of elements in all cosets is exactly the same. So I will show you that the amount of elements in the left coset is exactly the same as the amount of elements in the right coset, and coincides with the amount of elements in the subgroup H itself. So this is our plan. So I want you to know what kind of thing I'm going to prove. So I want to show you that the cosets form a partition. So the left cosets form one partition of the group G, and the right cosets form another partition, probably different one of the group G, because the right and left cosets are not necessarily the same. But so this
Excuse me.
Yeah.
What is that notation in the left? Like, yeah, these things.
This one. This means that G is the union of these guys, and these guys do not intersect of.
Okay, yeah, I see. Thank you.
Yeah.
Also, what does mean to alphas?
Oh, alpha go. This is just some index. Like you just name all the cosets, like the first one, the second one, well, and so on.
So we write it below the union?
Again?
So do we write it below the union like this symbol?
Yeah, it's just the union of all the cosets, and alpha just goes through all the cosets. It just enumerates them somehow. Well, so it belongs to some set. Well, assume that there is finitely many cosets. Then alpha goes from the first coset to the nth coset.
And also, what do these schemes mean with H and Q1H? I don't really get it.
Oh, okay. So what is a group? A group is a set with an operation. So this is the set of elements. So then what is a subgroup? Is a subset. So this part of this set is our subgroup H. Then what is a coset? Coset is a subset of the group G. So it's just a part of this set also. So so group is just a set. And now subgroup and its cosets are subset of the group G. And this picture shows how these cosets lay inside the group G. So what I mean, it's impossible to have something like this. So if you have a group G, it's impossible to have something like this. GH is like this, and G1H and G2H like this. So this is impossible. They do not intersect. So they just form a partition of the group G. But don't worry, I will formulate a claim. Here was like some explanation what's going to happen.
Excuse me, but isn't normal? But for a normal subgroup, like left and right cosets, they do intersect. In fact, they are the same.
No, here I mean two distinct left cosets do not intersect.
Oh, I might have misheard that. Excuse me.
Yeah. I mean, for this picture, the left two different left cosets do not intersect. This left coset may intersect some other right coset, or maybe several right cosets. That's perfectly fine, because like these are two different partitions. But if you take just left cosets, they form a partition, or if you take just right cosets, they form a partition. So this is what I want to prove. But just in case there was a question regarding these pictures, is it clear now what the pictures mean? Or
yes.
Okay, cool. So let's try to formulate precisely what I meant by drawing all these pictures. So suppose G is a group and H is a subgroup. So this is a group and this is a subgroup. And we have two elements, G1 and G2 are two elements of the group G. Then we have two options. The option number one, either G1H is equal to G2H, or the option number 2, G1H doesn't intersect G2H. So this is exactly what's written here. So if you have two cosets, they are either the same or they do not intersect each other. So this cannot happen. So this is the claim. Are there any questions regarding the claim, the statement of the claim? Okay, so this claim proves that left cosets form a partition, and there is exactly the same claim for the right cosets, but I'll skip it because the claim itself and the proof are well, can be formulated in exactly the same manner. So I believe everyone can do this. So let's prove this. So let's take these two cosets. Well, if they are the same, so if they are the same, then this is the option number 1. So we may assume that these two subsets are distinct. So now we want to prove that in this case, they do not intersect. So let's assume that the contrary holds. Suppose, suppose that G1 does intersect G2. This means that there is an element here. So G is an element of this guy, and G is also an element of this guy. But what does it mean that G belongs to G1 times H capital? It means that G is equal to G1 times H1, where H1 is an element of H capital. From the other hand, G must be of the form G2 times H2, where H2 is an element of H capital. This is just by definition what it means, that G is inside this guy or inside this guy. And since this thing is G and this thing is G, then G1 H1 is equal to G2 H2. And now I want to multiply the okay, and now I want to show that this actually implies that G1H is equal to G2H. And if I show this, this will be a contradiction with what? With our case, because we assume that they are different. So the only thing that we need to do is to show that this holds. This is what we need to show. So this is what we have, and this is what we want to show. Just in case, are there any questions until this moment?
So why, if we prove this implication, we get a contradiction once more? Sorry.
Okay, so we assume here that we have two different cosets, and here we have that they are the same cosets.
Yeah, right.
So this is a contradiction exactly. Okay, so how to prove that? Okay, the cosets are subsets. So how to prove that these subsets are the same? We need to prove that the left-hand side is a subset of the right-hand side, and vice versa, the right-hand side is a subset of the left-hand side. So we need to show that G1H belongs to G2H, and G2H is a subset of G1H. I'll show you the first one. The other one is done in a similar way. So let's show that this guy implies this inclusion. So, okay, so in this case, I can multiply the equality, I mean this equality, by H1 inverse on the right. So let's multiply this by H1 inverse on the right, and we will get that G1 is equal to G2 H2 H1 inverse. Now, how to prove that this guy belongs to this one? We need to take an arbitrary element here and show that this element is actually here. Okay, let's take an arbitrary element here. It's simply, well, an arbitrary element inside the subset is of the form G1 times H. This is just an arbitrary element here. And how to prove that this guy is here? I need to represent this element in the form G2 times something from H. So let's do this. Now, because of this equality, I can substitute the right-hand side of this equality instead of G1, and I will get G2 H2 H1 inverse H. And as you can see, this element is represented as G2 times something, but all the elements here, H, H1, and H2, are elements of H capital. And since H capital is a subgroup, take an inverse and multiplying them gives me an element of H capital. So this guy is also inside H capital, and this is just G2. So by definition, this element is inside G2 times H capital. So, well, this is exactly what we wanted. So we started from this equality, and we show that each element of this subset is an element of this subset. So this inclusion holds. In a similar way, you can show that the other inclusion holds, and this completes the proof that these two cosets are the same. Are there any questions regarding the proof? Should I repeat something or clarify the details?
It's not really clear for me why, if we have H inverse, it implies that G1 equals G2 times H2, etc.
This one. So how did I get from this equality to this one? Yep.
Oh no, it's really clear. I just okay.
Yeah.
Never mind.
You just multiply here, and that's it. Okay. Are there any other questions? Cool. So now, from this moment, we know that the cosets form a partition. Another question. Well, also, as you may notice here, that different elements G1 and G2 may give you the same coset. For example, well, let's recall an example. If you take G to be Z and you take H to be 2Z, this is a subgroup of Z, then you may take 0 plus 2Z, or you may take 2 plus 2Z. These are two cosets of the subgroup H, which is 2Z inside the group G. But they are exactly the same. So the elements here are different, but these different elements give you exactly the same coset. So the name of this generator here is, well, generator is a bad word here. So this element here is not uniquely defined, is not uniquely determined. So in general case, if you have a group G and a subgroup H, it may happen that two elements are different, but their cosets are exactly the same. So the question is how to determine that two different elements give you exactly the same left coset or right coset. So I want to address this question now. Okay, so let's see. Well, if we have G1H, well, let me formulate the answer first of all. So the claim. This is our context. So we have a group G and we have a subgroup H, and we have two different elements. Not necessarily different elements, but we have two elements. Then G1H equals G2H if and only if G1 equals G2H for some element H from H capital. So if these two elements, well, this is exactly what's written here. So this is a criterion. So if you take an element, let's say G2, and multiply it by an element of H on the right, then you will not change the left coset. And this is the only way to get exactly the same coset as before. So this is how you check. For example, before giving a proof, let's demonstrate this on an example. So if you take Z to be a group G, H to be 2Z, then M plus 2Z equals K plus 2Z if and only if M is equal K plus 2 times something. So, which means, well, there is a different way to formulate this, which means M minus K belongs to Z. So this is the criterion. So, which means if M and K are both even or odd at the same time, their difference is also is always even. But if M is even and K is odd, or vice versa, then the difference is odd. So in the first case, the cosets are the same, and the second case, the cosets are different. So this is the way how to check if two different cosets are the same. This is an example how to apply this claim.
Little question about the remark.
Yep.
Don't we also need to write that like 2t belongs to 2z, like
what again?
2t belongs to 2z. M equals to k plus 2t in the right.
M
Equals to k plus 2t.
This is Z, not
no, in the right, like more to the right.
Oh,
like
2t.
Little
Okay.
m, yeah, 2t, and 2t belongs to 2z.
Oh, but 2t by definition belongs to 2z because t is an
like
integer.
T belongs, yeah, I see.
Yeah, we need to say that t is an element of z,
I'm
but this
talking
is
about
what I
that exactly.
assume. Yeah. But I mean, when I write arbitrary elements, I assume that these elements belong to the entire group. Here, the group we fixed is Z, so all elements are taken from the group Z itself.
Yeah, that's clear.
Okay. Okay, so let's prove this. Well, actually, the proof is exactly the same as it was inside the proof of the previous claim. So, well, if G1H equals G2H, then, well, what does it mean? It means that element G1, well, by definition, element G1 belongs to the left-hand side. So since the left-hand side is the same thing as the right-hand side, G1 is in the right coset. Well, I mean, I hope it's clear what I mean here. So, but what does it mean that G1 belongs to this coset? It means that G1 is of the form G2 times H for some element H. Okay, so this proves the implication from the left to right. And if we want to prove it from the right to left, so we need to take G1 to be equal to G2 times H, and we want to show that these two cosets are the same. And this is exactly the same proof. So we want to show that G1H is a subset of G2H, and we want to show that G2H is a subset of G1H. So this is what we want to prove. And here we take, well, let's try to prove the second one. So I want to prove the second one, and the first one will be left as an exercise. So I take an arbitrary element G times H from this coset. Then, using this equality, I write, let's say H prime, because there is a collision of names. So I take an arbitrary element G2 times H prime, and I rewrite this as G1 H inverse times H prime, because here I can divide this equality by H on the right, and I will get G2 is equal to G1 times H inverse. So I can substitute this by this thing, and as you can see, this guy is of the form G1 times something from H capital. So this means that this guy is inside G1 H capital. And so we have checked that an arbitrary element of this coset is inside of this coset, and that's it. So the other inclusion can be proven in exactly the same manner. So, and also you may reformulate this in the other way. So G1H is equal to G2H if and only if, well, what do we have? We have like G1 is equal to G2 times H, but you can also reformulate it as G2 inverse times G1 equals H. But this simply means that G2 inverse times G1 belongs to H capital. So this is a different way to reformulate this criteria, how to check if two cosets are the same. Just in case, are there any questions regarding this?
Can you repeat the idea, please?
The later one.
The idea of the proof.
Oh, the idea of the proof. Okay, well, the idea is simple. Well, when you go from the left-hand side to the right-hand side, you just go by the definition. You take an element G1. It belongs to the left-hand side by the definition, so it must belong to the right-hand side. And the fact that it's a part of the right-hand side, well, can be expressed in this equation. Yeah, and when you go from the right-hand side, from the right to the left, well, using this equality, you want to show this equality. In order to show this equality, you need to show this and this inclusion. And here I'm showing how to check the second inclusion. So.
Okay. Yeah, it's clear.
Okay, cool. No problem. Okay, so let's proceed into a more interesting world. So the next claim, well, then is this. So I want to show you that all cosets have exactly the same amount of elements. Okay, so G is, okay, let's say, oh, just give me a second. Oh, I have realized that I have like -5 minutes left, and I haven't finished what I wanted to complete today. Okay, so that's a shame. Just in case, don't you mind if I steal like 10 minutes in order to complete the lecture, today's lecture?
No problem.
Okay, I'm sorry for this, but I was sure that we need to end at 18, well, at 6 p.m. But yeah, we have to finish like 6 minutes ago. Oh, that's, yep. It's awful. Okay, so the claim. If I have a group G and a subgroup H, and suppose that H is a finite subgroup, then for every element G, the amount of elements in the left coset is exactly the same as the amount of elements in the subgroup H itself, and it's exactly the same as the amount of elements in the right coset. Okay, so now how to prove this? Let's consider a map on the group G, which takes element X to the element G times X. Well, I claim that this map is a bijection. Why? Because there is an inverse map which takes Y to G inverse times Y. So this is the inverse map. So if you take X, it takes it to G times X, and then G inverse times G times X, you will get exactly the same element. So this is a bijection. Multiplication by G is a bijection. But now, if you apply this map to a subgroup H, it goes to the coset G times H. And since the map was a bijection, it provides a bijection between H and G times H. So the latter means that there are exactly the same, well, the amount of elements in H and its left coset G times H is exactly the same. The claim for the right coset can be proven in a similar way. So we have exactly the same amount of elements here. So now, if we know this, we can do better claim. If G is a group and H is a subgroup and G is a finite group, so we have finitely many elements, then the claim number one, the amount of left cosets is equal to the amount of elements in G over the amount of elements in H. So in particular, the amount of elements in H divides the amount of elements in G. And the second claim, the amount of the right cosets is also exactly the same number. So if you have a finite group and its subgroup, then the amount of left and right cosets is exactly the same and can be computed by this formula. And in particular, this formula means that the order of the subgroup divides the order of the group. So the amount of elements here divides the amount of elements here. So this always happens. So how to prove this? Well, as we already know, all cosets form a partition. So since we have finitely many elements, there are finitely many distinct cosets. So suppose these are all possible cosets for the group H. Then the group G is just a disjoint union of these cosets. So you may write these pictures like this. But then you may compute the amount of elements here, like the amount of elements here plus the amount of elements in the other coset, etc., etc. So the amount of elements here is just this thing, because they do not intersect each other and they cover the whole group. But because of the previous claim, the amount of elements in each coset is exactly the same as the amount of elements in the subgroup H. So this will be this guy times the number of left cosets. So this completes the proof. So as you can see, this integer equals the amount of elements in H times the number of left cosets. So the number of left and right cosets must be exactly the same. So the left cosets and the right cosets, they may be different, but the number of the left and right cosets is exactly the same. So you may formulate, we may give another definition, which says that if we have a subgroup in a group, so this is a group and this is a subgroup, then, and if the group G is finite, then the number of, so we will define an index of the subgroup H, index of H, to be the amount of left or right cosets. So this is the amount of left cosets, or which is the same, the amount of the right cosets. So it doesn't matter which one we choose. So this is just an integer. And there is a famous Lagrange theorem which says that if you have a finite group, this is a group and this is a subgroup, then the amount of elements in the group G is equal to the index of the subgroup H times the amount of elements in the subgroup H. So this is the Lagrange theorem. Well, it has several useful corollaries, but I believe I'll discuss the corollaries the next time. And so this is the place where I want to stop. So are there any questions regarding the lecture?
Yeah, so can I ask a question about an example that you provided about like 2Z is a subgroup of Z?
Okay, 2Z is a sub. Okay, let's go. Okay, it was somewhere here. Or probably not.
Yeah, right.
Okay.
So I wanted to ask, like, for example, as I understand, а можно по-русски, да, уже закончилась лекция?